So the term trigonometry is from the Greek words meaning triangle measure. Trigonometry has been around forever, but and it hasn't really changed that much. It helps us in a ton of application problems. A lot of your physics problems come from trig. If you're doing like force and all those fun things, you're using trig. When you do bearings, I don't know if y'all are going to get to that, but you're going to use trig. I mean, it's all trig. When they survey land, they're using trig. When they put a rocket into space, they're using trig. So trigonometry is really everywhere. Couple terms here. Initial side, terminal side. This is true with any angle, like when we did angles in geometry. Initial side's where you start, terminal side's where you end. When you're on a coordinate plane, your initial side is going to be this positive x-axis here. Standard position is going to go clockwise from there. So clockwise is going to be your positive direction. Counterclockwise is going to be your negative direction. So like from here, if I did 120 degrees, I would assume I'm going counterclockwise 120 degrees. If I said negative 68, I would assume I was going clockwise, negative 68. So counterclockwise, positive, clockwise, negative. All right? Always starting from here. Initial side, terminal side. That's how it will be from here on out, right? Anytime you're on the coordinate plane. So let's look at just a couple things here. One way in which we use these types of measurements is bearings for ships. By bearing, they mean direction, okay? And so when they're given this type of bearing, they are talking about in standard position here. But for a ship's bearing, it's a little bit different. When you see the word bearing, they didn't say standard. They said the ship's bearing. And so when you're talking about navigation, this is one more way of doing this. And for navigation, you start due north and go clockwise. All right? Due north and go clockwise. And so if you see in your book, they actually have it drawn a little bit differently than standard position. And the reason they do this is all of your directional is based on north. And so for this guy, they want us to represent his in standard position with an angle measure. Now you'll notice that we have a degree measure here, right here, but these do not have degree measures. These have little dashes, all right? These represent minutes and seconds, all right? So there are ways to convert that to a degree in decimal form. And then there's a way to figure out exactly where it is on the coordinate plane. But if I were to just draw this, sketch it, let's say I were to sketch this, then I would say this is somewhere between 127 degrees and 128 degrees, right? So if I were sketching this, I would say somewhere. Now, standard position would tell me to start here and go this direction, 127 degrees. But bearing for a ship actually tells me to start due north, which hopefully all of you know where north is. And it tells me to go clockwise, all right? So a couple things I want to point out before we do this one. If it is in standard position, then you are going to start at the x-axis and you are going to go counterclockwise for positive, clockwise for negative, all right? If you see the word bearing, like navigational, unless they tell you otherwise and actually say the word standard, all right, then you are going to assume that you start at north and go clockwise, all right? Now, keep in mind, with bearings, they will sometimes say east-west as well, okay? And so if they said a bearing of east, due east, or due west, then that actually tells you from north which way to go. But if they just tell you the bearing, then you're going to assume start at north and go clockwise, all right? And so pay attention to your terminology when you start getting into word problems. The main focus here, though, is to convert this guy. So we're actually going to convert him from seconds and minutes, or minutes and seconds rather, to degrees with decimals, all right? And so we already have the whole degree, that's 127. We need to transfer this 30 and 9 into decimals, all right? And so we are currently in minutes here. That's what this little 1 dash means. And we want it to be into degrees. Well, how many minutes are in an hour? 60. And so that's how many degrees are in. That's how we do our conversion here. So if we are doing minutes and seconds, you can think of that as minutes. 1 degree for every minute. And so you would actually take that and divide by 60. And you would get what? You should get 0.5, right? 30 times 1 over 60, right? Makes sense? All right. We have 9 seconds. All right. Well, we have to convert it to minutes and then to seconds. So we're actually going to take that 9 and divide by what? 3,600, right? 60 and divided by 60 again. And so if you divide by 3,600, what do you get? Hopefully that. All right. And so if I'm going to convert, I am going to add all those up. All right. So I'm going to say 127 plus 0.5 plus 0.0025, and I'm going to get 127.5025 degrees, which is a crazy degrees. All right. Now, again, if I'm just sketching this, I'm going to sketch it somewhere around here, right? I mean, that's about where he is. I'm not doing it exactly. But if I am navigating a ship for a long distance and I'm off by even seconds over a long period of time, I'm going to get to the wrong destination. So that's why with bearings, they go out that far. All right. It seems like this is a lot of decimals when you're talking about degrees, right? But the fact is, when you are going a long distance, the further off you are, the further you go, the further that angle is going to be off. Like just the slightest amount of angle measure difference, the further you go, right? You can see how far apart you are at the peak of that, right? And that's why they're so specific with navigation, with aeronautical, right? They're going to be a lot more specific than if we're just walking across a room. The longer distance you go, the more specific you need to get with your bearing, all right? So if I am going from minutes to seconds, I am going to divide. So then if I'm going from the other direction, I would do what? Multiply. So if you're given a decimal, you're going to need to multiply. And you need to do it in steps. So you'll notice that I did it in steps here. I did this piece first, and then I did this piece. You do the same thing when you're going the other direction. If I am given something in decimal form, I would actually multiply that by the 60 first, and then get another decimal and multiply the other decimal by the 60 again. And so you do it in steps. And I'm actually going to have you do it the other direction. Try this one. Negative 2.87. We want that with minutes and seconds instead of decimals, degrees. All right, so this should be a review topic. The radian measure of an angle, theta, is the ratio of its intercepted arc length, s, to the circle's radius. Theta is s over r. A central angle that intercepts an arc whose length is the same as the circle's radius has a measure of 1 radian. So think of radian as the linear distance that you travel in a circle, and your angle or degree is the angular measure that you travel, right? And so you really can't do, and so any of your measurements that you get to, they're going to want it in radians, because radians is going to be this little guy right here. Okay, and so if you are talking about, in this case, which we'll get to as the unit circle, this would be 1. But if you're talking about this in radians, we're not just talking about the degrees that we moved. We actually want the linear distance that it moved over the radius. And so there's an easy conversion, because if I were to travel a complete circle, okay, a complete circle is going to be 360 degrees. We all know that. Well, in radians, a complete circle is 2 pi. All right, which makes sense, because if I'm talking about circumference, right, what is circumference? Well, it's 2 pi r. Well, radians is that distance divided by r. Well, if I take 2 pi r divided by r, I get 2 pi, right? And so a full circle in degrees is 360. A full circle in radians is 2 pi. A half a circle in degrees is 180. A half a circle in radians is just pi. And so you get this conversion ratio, pi over 180, 180 over pi, which is how you go back and forth between degrees and radians, okay? And so that's where we get our conversion. If I have degrees, I want radians, well, I'm going to do pi over 180. If I have radians and want degrees, I'm going to say 180 over pi. You always want to get rid of what you don't have. And so pi radians over 180 degrees or 180 degrees over pi radians will be your conversion. So if you look at this example here, convert these each degree measure to radians and each radian measure to degrees. You literally just do your conversion. So this first one that they've given us is in degrees. I know this because I have the little degree symbol, right? And so I have it in degrees. I want it in radians. That means what I'm trying to get rid of is going to be on bottom. What I want is on top. And you literally just multiply. So pi over 2. Same thing with negatives. Just pay attention that you put your negative in your final answer. Again, I know this is degrees because I have a little degree. So when you reduce this, by the way, you get 5 pi over 4. Make sure you know that that's negative 5 pi over 4. That tells me the direction that I moved. All right, these last two are in radians. How do I know? How do I know they're in radians? Because I'm talking about an angle and I have no degree symbol. Okay, so this is radians and this is radians. He does not have a degree. Just because it doesn't have a pi doesn't mean it's degrees, okay? You have to have your degree symbol for it to be degrees. So for these, I'm going to flip it. This was 2 pi over 3. Instead of pi over 180, I'm going to say 180 degrees over pi. Most of the time, which is why the last one looks weird, you'll see that pi in your original and it's going to cancel out, right? Cancel out. You can reduce this guy. Right, you're going to get 120 degrees. For this one, you don't have a pi to cancel. So we have 6 times 180 over pi. And you get this crazy 1080 over pi, which is a weird radian measure. But they put it in decimals, 343.8 degrees. But your answer here needs to be degrees. Coterminal angles, exactly what it sounds like. Terminal, where something ends. Coterminal, where two things end at the same time, right? I mean, that's what it means, coterminal angles. And so because you can go either direction and because this is a cyclic function, right? It's a cycle. You can keep going around. It's not like your biggest measurement is 360 degrees or 2 pi, right? And so you will have the same exact ending point for multiple angles. They are coterminal. They end at the same point. So if I were to look at this guy right here, negative 4 pi over 3, there is an angle over here that ends at the same point, right? If I were to look at, which they give me this one here, I guess, as an example. If I were to look at this angle measure of 300 takes me 90, 180, 270, and 30 more degrees right here to 300. Well, if I were to go negative 60, I would actually end at the same point, right? These are coterminal angles. And so you can actually go either direction. The easiest way to find a coterminal angle is to add a circle to it, all right? So if I were to take, or to subtract a circle from it, if I were to take this 300 and add a circle, I would get 360, right? Plus 300, 660. That means I could go all the way around to 660 and end up here. Or like they did, 300 minus 360 gives me a negative 60. So adding a circle or subtracting a circle is the way to find a coterminal angle. And very often they will do it like these instructions here on this example. Write an expression for all angles that are coterminal, then specify one positive and one negative coterminal angle. Well, how would I write an expression to represent all of them? Well, I would say I need to take my negative 4 pi over 3, and I need to add circles to it. Well, we know circles are what? 2 pi, right? Do I know how many circles? Well, it wants all circles. So I'm going to say, well, some number n times 2 pi. 1 times 2 pi, that would add 1 circle. 2 times 2 pi, that would add 2 circles. Even if I put negative numbers, that would go the opposite direction, right? And so this represents every single angle that is coterminal with negative 4 pi over 3. Now it wants me to actually give an example. So if I want a positive and a negative coterminal angle here, I'm going to take negative 4 pi over 3, and I'm going to add a circle. Am I in degrees or radians here? Radians. What's a circle, a complete circle in radians? 2 pi. And I'm going to put over 1 because these are fractions. What do I need? Common denominator. What is my common denominator? 3. So instead of 2 pi over 1, I'm going to say 6 pi over 3, right? And I'm going to add it. Negative 4 pi over 3 plus 6 pi over 3 equals what? 2 pi over 3. That is a positive coterminal angle, all right? They also want a negative coterminal angle. I'm going to say negative 4 pi over 3 minus 6 pi over 3. What is that going to be? Negative 10 pi over 3. That is a negative coterminal angle. Add a circle, subtract a circle. If you're in degrees, add 360, subtract 360. If you're in radians, add 2 pi, subtract 2 pi. All right? Coterminal. When they want arc length, your circle is a complete circle. If you take a piece of a circle, you get an arc, right? I mean, we've all seen them. They're on top of stuff, whatever. It's an arc, all right? They want the length of the piece of the circle. Well, they typically want this in radians always, because remember, if it's in degrees, we're talking about an angular movement, not a linear movement. And so anytime they're asking for a measurement, they're going to want it in radians, which means if it's not in radians, you need to convert it to radians. And you'll also typically see theta referred to when they're talking about in radians. Not always, but typically when you see theta, they're talking about it in radians. Theta is just a Greek letter like XYZ. It's a variable, okay? But standard wise, when you see theta, they're talking about radians. But every once in a while, you'll see theta and they'll keep it in degrees. But, for this right here, the reason theta is in your formula, theta is just representing your angular measure in radians. That's what they mean. R represents exactly what it means, radius. That's what R always means when we're talking about circles. And so if you want to find the arc length, you're just going to take your radius times your angle measure in radians. All right, so let's look at the example here. 1 minute of latitude. A nautical mile has historically been defined as 1 minute of latitude. That's a nautical mile. At the Earth's equator. Determine the relationship between a standard mile, and a nautical mile, given that the Earth's average radius at the equator is 3,959 miles. All right. So they technically gave us this in degrees, but they gave it to us with minutes and seconds versus decimal degrees. Does that make sense? So when you see the term minute, they actually are giving it to you in degrees. which means we need to convert it to radians. But before we convert it to radians, we need to get it in decimal degrees, not minutes and seconds degrees, okay? So you're going to take what you did on the very first problem, convert it to decimals. Then you're going to take that guy and convert it to degrees, all right? So I have it in minutes. What did I divide my minutes by? 60. So instead of writing 1 minute, I'm going to say 1 over 60, okay? So I'm going to say 1 over 60, all right? That's how they gave it to me in degrees. However, in order to put it in my formula, S equals R theta, which is what they've given me, I need this guy not in degrees, but in radians. How do I convert this guy to radians if I have it in degrees? I multiply by what? By pi over 180, all right? So the first thing I did was take it from minutes and seconds to decimal degrees. Then I converted it to radians by pi over 180, okay? So this right here represents my theta, okay? That represents my theta. What do I need to multiply my theta by? My radius. What is my radius? There we go, 3,959. This they will give you in decimals, by the way. They are rounding to the nearest hundredth. So take this, 1/60th times pi over 180 times 3,959 and see what you get. Rounded to the nearest hundredth place. I would not round in the process, by the way. I would put it all in. You can either put it in parentheses like this, or you can multiply all your numerators and divide by all your denominators. Divide. Either way, you should get approximately what? 1.5. So 1 nautical mile equals approximately 1.15 miles. So, uniform circular motion. It analyzes the linear and angular speeds of an object. Those are two different things. Linear speed is how far it's actually traveling if you were to stretch it out with a string. Okay, that's linear speed. We think that linear speed is what we use for like miles per hour, right? That's how far we're traveling down the road. That's your linear speed. Circular or angular speed is how much you're moving in angles or in radians, really, because you're going to convert all this to radians, all right? So these are typically done with something that spins. They like to use bicycles or I think this is a vinyl record, how far the needle moves or whatever. They'll use, I think the one that you have as an example is a buffer, a spinning wheel on a buffer. And so something is spinning and they want to know how much it's moving in angulars, right? Angular movement. And then they also want to know how much it's traveling. How much is it actually traveling if it were linear? And they've given us two formulas. Theta is the radian measure of the angle of rotation. The angular speed, this little thing that looks like a W is the Greek letter omega. All right, omega. That should sound familiar in biblical terms, right? When you use it for God, it's capital letter Greek, not lowercase. This is lowercase, but whatever. Alpha and omega we're familiar with, beginning and the end. So this is the last letter of the Greek alphabet in lowercase. It looks like a W. It equals theta over T, T being time here. Okay, they will give you some time in minutes, seconds, hours, and sometimes they'll want you to convert that, so pay attention. Because sometimes they'll say it's going this many revolutions per minute, how far is it in miles per hour or something, right? And so pay attention to your final answer, what they wanted in, because you may have to do just your basic conversions like you've learned way back in like pre-algebra. But omega equals theta over time. That is your angular speed. Theta is always going to be in radians here. So if they give it to you in degrees, again, you're going to have to do a conversion. Linear speed. Linear speed is going to be represented with this V. V is going to represent your linear speed, which is what we typically use for linear speed. And it is S, just like we found in the last problem. Remember, S was your radius times theta, okay? S over T. S over T. So, you'll notice that they also had R times W is another way to write this. Why would they write that? Well, if you were to say, what is S? S, we found out in the prior one, is going to be R times R theta, right? So we have S over T here. W, that little W, which is your omega, equals theta over T. And so they also have that you can say, well, it's just R times your omega. Because if you were to replace these guys, you would end up with this times that, the R, and you end up with just R times your theta. And I wrote it as not theta. R times your omega. If you were to replace it, you're going to see that these guys can be replaced. So, you can do this either way. You can either do your S over T and just solve this guy by doing R times theta, or you can go straight to the R times omega if you've already solved for your omega. All right, so sometimes they ask for both. And if you already have your omega, just plug it in to find your linear speed, which is what we're about to do. You already have the over T right here, but because he's already over T and S is R times theta, you could just literally multiply both sides by your R. The reason this helps you is a lot of these problems will say, what is the angular omega? And then what is the linear, the V? And you've already solved for the omega, just multiply by the R and you're already there, right? Versus going back and calculating it a different way. You're already at that point. All right, so they've given you both of these. All right, let's look at this. Analyzing. Karen is playing a vinyl record at 33 1/3 RPMs. By the way, when you see RPM here, there we go. They spelled it out for you. On her vintage record player, determine the angular speed of the record in radians per second. What did they give it to you? In revolutions per minute, okay. Then find the linear speed in inches per second. They are just driving you crazy with these, right? Inches per second. I will say you will have already converted to seconds, so we're good to go. All right. The point of the edge of the record is 6 inches from the center, and the linear speed at the point of the edge is 2 inches from the center, okay? So they've told us a couple things here. The angular speed, then find the linear speed at the point, and the linear speed from the edge of the label. So they want 2 linear speeds. Now here's the thing. Once you found your omega, what are we doing? We're just going to multiply by our radius. You'll just have to do it twice. One for the one radius, one for the other radius, okay? So let's talk about revolutions. What does revolution mean? It goes in one complete circle, correct? It goes in one complete circle. They actually didn't give us angle measure at all. They gave us revolutions, okay? And so we have 33 1/3, and I will tell you, 33 1/3 is horrible because 1/3 is a repeating decimal, right? So what they did, which is a smart way to do this, is they multiplied by 3. So it would be 33 1/3 revolutions per 1 minute, right? But that's hideous. So they just multiplied the top and bottom by 3. Why do you think they did that? Get rid of your repeating decimal. So that ends up being 100 revolutions per 3 minutes. That's much prettier, by the way. Don't you think? Yes? All right. But what we have to figure out is we need it in radians. A revolution just tells us how much it goes around. But one revolution is one circle. We have 100 per 3 minutes. So what are we going to multiply the one circle by if we want it in radians? What is one circle? 360. And in radians it is 2 pi. And so I'm going to take this and I'm going to say, well, this is going to be 2 pi radians for every one revolution. And that will give me, instead of revolutions, now I have radians. So I've gotten that one out of the way. I now am going to have it. Take out my revolutions. I am going to have radians. They gave it to me in minutes. What do they want it in? Seconds. I have to do a second conversion here. All right. So I do not want minutes. Right now my minutes is in my denominator. So that's going to go in my numerator. I want it in seconds. What is the number of seconds per minute? So this will be 60 seconds. So now I double check and say, okay, that will cancel out my minutes and that will give me radians per second. That is what I want. Radians per second. All right. Radians per second. So this will represent my angular speed. I have my theta and my time, right? My theta is what I'm solving for when I solve that revolutions. And my time was 3 minutes. Now I'm going to have it in seconds, which is what I wanted. So this is going to give me what my omega is. This will give me my omega. I am multiplying my theta divided by my time. Multiplying my theta to get it in radians, and it's being divided by my time, which will eventually be seconds, okay? So this is my omega. And when you solve it, you get about 3.49 radians per second. That is my omega. That is my omega, okay? 10 pi per 9 seconds, by the way, is the exact. 10 pi per 9 seconds is the exact, and I'm saying that because we're going to use the exact when we actually calculate the linear, okay? Which I don't think is going to be too far off if you plugged it in, but... So for the first linear, they want us to use 6 inches. So what am I going to do? Well, I'm going to multiply 6 times my omega. And you're going to get approximately 20.94 inches per second. The second one they want us to find is if it were 2 inches away, we're going to take that same omega that we found and multiply it. We're going to get approximately 6.98 inches per second. So we found our angular speed. 3.49 radians per second is how far it's moving angular. 6 inches away from the center, it's moving at 20.94 inches per second. 2 inches away, it's only moving at 6.98 inches per second, which makes sense. The closer you are, the less it's traveling, right? In the same amount of time. This is an area of a sector. So we talked about arc length. That is the piece of the circumference, right? So the arc length is r times theta. But area of the sector, so think of it like the crust of the pizza. That's the arc length. The sector is the whole slice, right? You're trying to find the area versus length. So it's two-dimensional when you're finding area. And so this formula is written differently in your book. In your book, it is 1/2 r squared times theta, I think is how they write it. So 1/2 r squared times theta. Keep in mind this theta is in terms of radians, not in terms of degrees. So if it is in degrees, you have to do pi over 180, all right? In pre-cal world, we learned degrees over 360, which is actually that 1/2 piece of it. Pi, you're actually changing it to radians and you don't even know it, r squared. So both of them work, actually. Here, they actually tell us if the shaded sector has an area of 24 pi meters squared and BA is 12 meters, find the radian measure and the degree measure of the triangle. All right, so in this case, they actually gave us the area. And so we're solving backwards here. We're going to plug in what we know, solve for what we don't know. So here we would plug in that 24. That is the area. 1/2. B to A is the radius. So we have 12 squared theta. All right. And so you would divide it out, simplify, right? 12 squared is 144 over 2. So this is going to be 72. So divide by 72. They did not divide by 72. We'll just ignore that. You end up getting pi over 3 when you reduce that guy. That is in radians, so that answers part of it. Find the radian measure. This is the radian measure. They also want degrees, so 180 over pi. Pi over 3 is 60 degrees. That's both radian and degree measure. On